So I will continue with kernelization. So the second part, and my plan is now the following. So I will speak about so all kernelization which will be today will be running around two old and fundamental theorems from graph theory. And on top of that, I will be building several different techniques. So I will speak about crown decomposition, and I will give a kernel for vertex cover and for max SAT. That will be one application. Then I will be speaking about Nemhauser-Trotter and about LP relaxation for vertex cover. That will be another thing. And still, the whole team will be around matchings and the graph and Koenig-Hall theorems. Then I will speak a little bit about expansion lemma, only one. And then, as an example of the application of expansion lemma, I will give a kernel for component order connectivity. Okay, so kernelization part 2. So all this talk will be around two basic theorems in graph theory, and perhaps the oldest theorem in graph theory. The first theorem is a Koenig's theorem from 1916, and basically it says that tau is equal to nu of graph G, or in other words, if I take a bipartite graph, the number of vertices in the minimum vertex cover in this graph is always equal to the number of edges in the maximum matching. So, and also there are efficient algorithms like Hopcroft-Kraft algorithm from 1972, which computes in this m number of edges, n number of vertices, so matching or a vertex cover of a bipartite graph. That will be one theorem which I will be really using all the lecture. And the second theorem is also Wholesome marriage theorem from 1935. Philip Hall, and so if I have a bipartite graph with a bipartition A and B, then graph G has a matching of A into B. If and only if for every subset of X, the neighborhood of X in B, the size of the neighborhood of X is at least the size of X. All right? This is it's a kind of theorem. And again, so Hopcroft-Kraft algorithms also can be used to either to find a matching which is of A into B in this time, or even to give a certificate why there's no such a matching, and this certificate is a set of inclusion minimal set X of A, which doesn't satisfy the condition of the whole theorem. Right? So, and everything what I will be doing today, once again, just will be coming from these theorems. Okay, so the first notion which will be very useful is the notion of crown decomposition. So crown decomposition of a graph is a partition of the vertex set of a graph into three sets: crown, head, body, with the following property. So the set C, the crown, is an independent set. The set H, the head, it separates the crown from the remaining part of the graph. So there is no H going from C to B. And there is a matching between C and H, which covers H. So there is a matching of H into C. Right, so here is example. So C is an independent set. I have so H separates C and B, and there is a matching from H to C. So, and why it's called crown decomposition, right? I try to make it in the picture. So this is the head, this is the crown, this is the body, right? This is okay. So let's see how we can use crown decomposition for vertex cover. Yes, so the argument is the following. So if I have a crown decomposition here, yes, so these edges between the crown and the head, they have to be covered, right? And because I have a matching from H to C, by conic theorem, the minimum vertex cover in this graph is equal to the size of the matching. So it's always the number of vertices in H. So to me, it doesn't make any sense to put in the vertex covers the vertices from C. Anyhow, I have to put in total so H vertices to cover these edges, which means that I just can put all vertices from H into vertex cover, delete them, and also forget about these vertices. So if I have a crown decomposition, then I can have a reduction rule. So I can delete all vertices from H and C from the graph and decrease my parameter by the size of the H. Okay? Okay, so this brings us more or less immediately to the key lemma. So if I have a graph G without isolated vertices and integer k, then in polynomial time, I can either find a matching of size k plus 1, find a crown decomposition, or conclude that graph has at most 3k vertices. So in the first situation, I know that there is no solution. I'm happy. In the second situation, if I find a crown decomposition, I can use a crown reduction rule. I reduce my instance. And in the third case, I know that I have a kernel with 3k vertices. Okay, so how to prove the lemma? First of all, I find a greedy maximal matching. If the size of the matching is at least k plus 1, I cannot cover this matching by a vertex cover of size k. In this case, I say no immediately, right? Okay, if I found a matching, a maximal matching of size less than k plus 1, then if I take the endpoints of the matching, what remains is an independent set, right? Because I cannot add any matching anymore to this set. Okay. Yes. So what I'm doing? So I construct a bipartite graph. So I take on one side I take all endpoints of my matching, and here is an independent set, and then all edges of the graph which are between them, so which exist between them in the graph. So this is a bipartite graph. Yes, and now I have to consider cases. So the first case, if I look at the vertex cover in this graph, and the first case is if the vertex cover of my graph contains at least one vertex of X. Now, I am using Koenig theorem, and I say, well, that this set X will give me a crown decomposition. So how come? So I have a bipartite graph. And I have a vertex cover, so part of the vertex cover lives here, and part of the vertex cover lives here. Now, what I'm saying that this part of the graph, it separates the neighborhood. So if I take this as a H, and I take this as the neighbors of H, then there's no H coming from here to here. Why? Because if there was H coming from here to here, this H is not covered by the vertex cover.
The fat black edges are the vertex cover?
Huh?
The fat black vertices are the vertex cover?
Which?
The thick black.
The big black edges are the vertices of vertex cover, right? So I say if at least one of the guys lives in the of the vertices of vertex cover lives in X, then I can take this vertices which lives in X and as a head of my crown decomposition, which means that these vertices, they separate the neighbors of these vertices, they do not have edges going down. Right? So this is a...
Capital H is the intersection between capital X and the vertex cover, you assume?
Say again. Capital
H is the intersection between capital X and your assumed vertex cover, which is visualized by thick.
Capital X is the intersection of the vertex cover of the bipartite graph intersected with no, capital X are the endpoints of the matching, right? And H is capital H is the intersection of the vertex cover with X, right? Then I say that the capital H separates. So if I take the neighbors of the vertex of the neighbor of H in I, then there's no H coming from this neighborhood, from the vertex neighborhood below. So this is Yes. So in this situation, I would be able to construct a crown decomposition. So what I will do, I will take this vertices as the head, this vertices as the crown, and this vertices as the remaining part of the body. And I claim that this is the crown decomposition. Why? Because this is in the independent set. So these vertices, they separate these guys from the remaining part. And there is a matching from H to C. Now, if I have a minimal vertex cover which contains only vertices of I, which lives here. So first of all vertices of I should be then in the vertex cover. Right? Because every H should be covered and I don't have isolated vertices. But then it means that there's yes. So then how many vertices can live in the set I? It cannot be more than k, right? Because my budget is k for the vertex cover. So it means that I have at most k vertices living here. And by my construction, there are at most 2k vertices living here. So in total, I have at most 3k plus 1 vertices living here, everywhere. Right? So once again, what I'm doing, I construct a maximal matching, and then if I look at the vertex cover in the bipartite graph, which is obtained by the vertices of the matching and the remaining vertices. Now, if in one case I am able to construct a crown decomposition, so I'm here, or in one case or in the other case, I know that the size of my graph is at most 3k. So this is exactly what Lemma was saying.
Why is the size of X is smaller than 2k?
No, it's a. So why the size of X is smaller than? Okay. So what is the X? X. So I construct a greedily matching, right? The matching is of size at most k. Right? It means that the set X cannot have more than 2k vertices.
So the drawing is slightly confusing. X contains a matching, we're just not drawing the edges. X are the endpoints of matchings.
Okay.
X are the endpoints of the matching set. Yeah.
K bluish edges inside X, and the endpoints of those are the small black.
Yes. But if I draw it like that, then that will not be a bipartite graph. So then again, it's yeah. Okay. So once again, so I'm taking the endpoints of the matching. I remove the edges of the matching, and between these guys, and then I just take this.
Edges within X are not drawn.
Yes.
Edges within I don't exist, and there's actually a dashed edge in the third picture, which I always can't see as dashed, but the diagonal edge in the third picture.
No.
Absence of edge.
And the diagonal dash h is shows that this h cannot exist.
Right. And if you have bad eyesight and they sit back in the room, you can't even see that it's there.
Okay.
There are
So
three different visualizations of edge on that side.
okay. So yeah. So it's too much packed there. So vertex cover. So basically it means that vertex cover admits a kernel with 3k vertices. Right? Yes. So another example is the max SAT of so how kernelization algorithms. So what is a max SAT? I have a CNF formula phi and I have a parameter k, and then I want to decide if there is an assignment satisfying for phi which satisfies at least k clauses. Right? Yes, and the theorem is that max SAT, it admits a kernel with k variables and 2 k clauses. Okay, so the proof. Well, first of all, we can assume that 2k clauses, we cannot have more than 2k clauses, right? Because we always have assignment which satisfies at least half of the clauses, right? You can use the random arguments, or you can use even deterministic argument to show that. So if you pick up a variable, and then, so you always pick up a variable which satisfies at least as many clauses as it's not satisfies, right? So it's so if we have more than 2k clauses, we are done, right? Now. Again, so if we have less than k variables, we are also done. There's nothing to prove here, right? Then our instance is already a kernel. Okay, suppose I have an instance. So here I have at most 2k clauses here, and I have at least k or more than k variables here. Now, if I construct a bipartite graph for this formula, right? So here are the variables, here are the clauses, and ages are if a variable belongs to the clause, then I put an age. Now, if there is a matching from here to here, we are done. Why? Because here I have at least k plus 1 vertices. So if I have a matching with of size k from left to the right, I can use this matching to satisfy this k clauses. Right? So every variable satisfies its own clause in this matching. So I satisfy k clauses, I'm done. Right? So suppose that there's no such a matching, right? Then again I try to use whole condition. So why there's no matching? It means that there exists a set C such that the size of C is larger than the size of its neighborhood. So I pick up a minimal set C which satisfies this condition. And I call, so let's the neighborhood of C be H. And now, so because set C is minimal, right? Then by whole theorem, what does it mean? That it means that if I take any vertex X or belonging to C, then every subset of C minus X will satisfy whole condition, right? So, which means that for any subset of C minus X, there will be matching of this set to the right. Right? So for any vertex X from C, there is a matching of C of minus X into H. Now, by my condition, I know that the size of C is larger than H, which means that if I have a matching from C minus X into H, it also means that this exactly matching is also of matching of H into C minus X. The sizes of this guy should be equal. Right? But this means that we found a crown decomposition here. So what's happening here? Look, view it this way. So I take this guy as a head, this guy as a crown, and this guy as the body. First of all, these are independent set, right? That's the way I construct the graph. Now, these guys, these guys are separated from the remaining part by these guys, right? Because Because these guys are the neighborhood of these guys. And there is a matching of H into C. This is what I prove here. So this is a crown decomposition. Right? So what can we do then? Yes. So once again, I have the variables here, and these variables, if you look at SAT, these variables, what they can control, the only thing which they can control, which they can satisfy, only the clauses from the head. Right? And they can do it, right? Because I have a matching from here to here. So these guys, they can satisfy these guys. And whatever assignment I put to these variables, they never influence the remaining clauses. Right? Because they're separated from them. Which means that what I can do, so I have reduction rules. So basically, I remove from my all clauses all guys which live in H. And I decrease my parameter by k minus h. This is right? Reduction rule. So once again, so what we assume? We assume that if we have at least k variables living here, then we can reduce the size of my problem. So this means that this is a reduction rule, which means that we apply reduction rule, and if you have a reducible instance, there should be at most k variables. There should be at most 2k clauses. Leaving here. Okay? So the other application or related result, again, around Hall and Koenig theorems, is Nemhauser-Trotter theorem. Yes, so let's just write vertex cover as an integer program, right? So what we want to do? So we have a constraint that for every h, at least one of the so at least one of the endpoints should be in the vertex cover, right? And we also we want to minimize the number of vertices in the vertex cover. This is a ILP formulation of the vertex cover. If I take relaxation of this ILP, I will get linear programming for vertex cover formulation. So I just omit the integrality constraints for this problem. So this problem we can solve in polynomial time, right? By linear program. And let's just see. So what can we extract from this problem, and what we can say about this problem for vertex cover just by looking at the linear program. Yes. So the classical results about this integer program of vertex cover is the following theorem of Nemhauser-Trotter. So suppose I have a linear program for vertex cover. So then I just take some solution for vertex for vertex cover LP, and then this solution, it partitions all vertices of the graph, or according to the values, the corresponding variables obtained in the linear program. So I put the vertices V0. This is the vertices which obtain the fractional values less than 1/2 in the linear program. V1 are the fractional values which obtains the value more than 1/2. And V1/2 are the values, the vertices which have values exactly 1/2. Right. So this is so far so good. And then the Nemhauser-Trotter theorem says that there is always a minimum vertex cover opt of a graph G, such that the opt is always between V1 and V1 and V1/2. In other words, there is always optimal solution which contains all V1 and which doesn't contain V0. Okay, so how this theorem can be proved? Yes, so we have a, so this is the solution of the linear program. This is the partition of the vertex set, or a partition of the variables. Yes, and suppose we have some optimal vertex cover solution which lives here, here, and here. Now I construct a new set of vertices. I call them opt prime. So opt prime, what is this? I take the optimum solution, the previous optimal solution, and then I take all vertices of the optimal solution from V0. I remove them, and then I take all vertices of V1 and I add them. So it's optimal solution minus V0 plus V1. So first of all, I claim that this set is a vertex cover. Why? Well, what is a vertex cover? My set is a vertex cover if and only if the complement is independent set. Right? So I claim that, so these guys, they should be independent set. Right? Because the previous solution was a vertex cover. Right, so these guys, they're independent set. And people, or not people, sorry. So the set V0 is also independent set. Why? Because if I have two vertices from V0, both of them get values less than 1/2. And the sum of them should be at least 1. So there cannot be, if they are adjacent, right? So there cannot be an H between them. So any two vertices from V0 cannot be adjacent. Which means that this is an independent set, which means that this is a vertex cover. Okay, so my next step is I want to show that well, this is a vertex cover, which means that the size of this vertex cover, because this was optimal one, right, should be at least this one. Yes, so if we have, if the sizes are equal, there's nothing to prove, right? Because now we have a vertex cover, which leaves between v1 plus v half 1, v half, right? So there's nothing to prove here. Okay. And now I claim that actually if the size of the optimum prime is more than optimum, then our fractional solution of linear program is not optimal. That will be a contradiction. Right? Okay. Suppose that it's not true. Right? Suppose that opt prime is larger than opt. So what I'm doing? Then I claim, well, if the opt prime is larger than opt, what does it mean? So how the set v opt prime and opt are different, right? So this is the set opt, and this is the set opt prime. So I take these guys and I put them here. Well, I remove these guys and I add these guys. So this means that the number of guys living here should be larger than the number of guys I remove, right? Yes. But then what I'm doing? Then, but if the number of guys living here is larger than the number of guys living here, what I want to do, I want to pick up a small epsilon to decrease the value of these guys a little bit here and increase the value of the guys a little bit here, right? So, and what I mean by picking a small epsilon, what do I mean? So here, all the guys living here, the values is larger than 1/2. So basically, there exists a small epsilon such that for any guy living here, its value minus epsilon will be still larger than 1/2. So the same here, all guys living here, their value is smaller than 1/2. So there is a small gap such that if I increase them a little bit, all of them still will be smaller than 1/2. So I pick up epsilon, which is smaller than this gap, here and here. Okay, so I increase all guys here by epsilon, and I decrease the value of all guys here by the same epsilon. And I claim that I still have a solution for linear program here. Okay, so what's happening here? Yes. This is what happened, and so basically to show that this is still a valid solution for linear program, I have to show that the constraint that the sum that for every age the sum of its endpoints is at least 1 is still holds, right? Okay, so I didn't. So there is no ages between A and B, right? Why? So there's nothing happening here, just because the opt was a vertex cover, so which means that A and B should be independent set. So there's no ages coming here, so I cannot damage any condition here. So the same thing, ages between B and C. What's happening here? Let's see, right? Well, so if I have an age, if I had an age here before, then the sum of the values here was more than 1. But I decrease one endpoint by epsilon, and I increase another endpoint by epsilon here. So the value remains the same on all edges going from B to C. And for the remaining parts, so from B to D, things are still fine. Why? Because the epsilon was very small. So this means that this guy was here more than 1/2. This guy is still here is more than 1/2. So still the sum will be more than 1. And so here it's also the same thing, the same type of argument. So again, I obtain still a valid solution for linear program by doing this. But the value of this solution is smaller than the value of the solution for linear program. Why? Because the number of vertices here, the size of this set is larger. The size of this set is smaller. And I decrease the value of my solution by the number of guys living here times epsilon. and I increase my solution by the number of guys living here times epsilon. So in total, I decrease the value of my solution. But I cannot do it, right? Because I started from the optimal solution for linear program. So so we built a linear LP solution with smaller value, which is contradiction. This is concludes the proof of Nemhauser-Trotter theorem. So, and a few remarks here. So the first remark here. So if I want to solve a linear program for vertex cover, I don't really have to. Well, we know that we can any linear program is solvable in polynomial time. But for this case, we can do much faster arguments, imply much faster arguments. So basically, we can reduce this problem to solving a problem of matchings in bipartite graphs. So we don't have to plug in all power of linear program here. So it's a one thing, and this is also much faster of doing this. So. And the second thing is also we will not be using this for kernelization things, but also it's also possible to show with a very similar arguments that actually a linear program for vertex cover always has an optimal solution, which is a half integer. So all values are in the range of 0, 1/2, and 1. But we will not use this for kernelization algorithm, so we don't need that. Yes. Okay, now I can improve their crown decomposition kernel from 3K to 2K by making use of Nemhauser-Trotter theorem. So what I am doing? Once again, so I write my problem vertex cover as a linear program, and then I run linear program. So this linear program gives me a partition of the vertices of the graph. And then what I'm doing, I'm just, as a kernel, I take all vertices from the set V1/2. So I delete V0 and V1. And then I reduce the parameter K by V1. And actually, I claim that this is a kernel, right? So this is a polynomial time algorithm. And we need to show that the size of this guy is at most 2K, and that this is a yes instance if and only if this is a yes instance. So first of all, why the size of these guys here is at most 2K? I know that my solution is of size K, right? And every guy here gives value exactly 1/2. So I cannot have here more than K plus 1 vertices, because that would mean that the size of my linear program is yes, that will be that I have no instance here. Right, so. Okay, so why the instances are equivalent? Yes, first of all, if I take vertex cover here of size K prime, then I claim that if I add V1 to this vertex cover, then I will have a vertex cover here. Well, why? Well, this is the same arguments, right? So the size of this vertex cover, of course, it will be K, because K prime is a K minus V1. And why is vertex cover? Because V0 is an independent set, right? So this should be the vertex cover. And in the opposite direction, so what's happening here? So if I have a vertex cover here of size K, then I take S prime as the vertex cover as the part of S which lives here, S cross V1/2. Well, I know that by Nemhauser-Trotter theorem there is always a vertex cover which is a subset of V1 and V1/2, which means that the size of this vertex cover is exactly K prime, K minus V1/2, or K minus V1. Right? So here I need to use Nemhauser-Trotter theorem. And besides that, yes, so this means that we have a kernel of size 2K. So any questions about vertex cover 2K, 3K kernels? Right? So the natural question will be if we can improve 2K to something even better, but this already becomes quite non-trivial, and most likely the answer is no. Okay, so the last tool which I want to discuss is expansion lemma. An expansion lemma is also a very useful and handy tool which is can be seen as a generalization of crown decomposition. Okay, what is an expansion in a graph? So I have a bipartite graph with bipartition A and B, and I have a set of edges going from A to B. And I say that this set of edges is Q expansion, where Q is some integer such of A into B, if every vertex from here is incident exactly with K edges of expansion of M, and then M saturates exactly Q times A vertices in B. So in other words, so what is the expansion? You have a set A, and for every vertex of A is a Q star, right? And the leaves of these stars, they are also completely different. So you really, it's like, if you look for K equal to 1, then this is exactly matching in a graph. But or the other way of looking at K expansion. Okay, that is a K expansion. And then there is just expansion lemma, which can be seen as just extension of a whole theorem. So there is a Q expansion of A into B if and only if for every set, a subset X of A, the neighborhood of X is at least Q times larger, Q times X. The neighborhood of X is at least Q times larger than the size of X. Right? And again, for Q equal 1, it's exactly the whole theorem. And again, and the proof of this, I will not give a proof, just a sketch what's happening here. So so the proof is really a reduction to the whole theorem. So you just duplicate, you may create K minus 1 copy of every vertex in A. So you have, for every vertex now, you have Q copies with the same neighborhood, and then you apply the condition of the whole theorem to this graph, and you will see that when you have matching in this graph, you will be able to construct Q expansion in that graph and other way around. So this is yes. And the tool which I will be using for kernelization is the following expansion lemma. So the formal statement. So if I have a bipartite graph with bipartition A and B, and Q is an integer, and this satisfies the conditions of the expansion. So the size of B is Q times larger than the size of A, and B doesn't have isolated vertices. Then I can always find an expansion, or I can always find a vertex set X and Y such that X has expansion in Y. Yeah? And this is also, there's a polynomial time algorithm. So in other words, so if you want to visualize this, what's happening here. So if I have bipartite graph with this condition that one part is Q times larger than the other, then, and there's no isolated vertices here, then I can always find a very specific crown decomposition. And in this crown decomposition, it's from the head, I have a Q expansion to the crown. Right, so in crown decomposition, I had only matchings here, but in this type of decomposition, I have a set of guys. So yeah, so this is an expansion. Yes, and my application here is the following problem. So I want to give a kernel for the component order connectivity problem. So I have a graph G, integer case and L. And now I want to find a set of vertices of size at most K, such that when I remove these vertices, every connected component of the remaining graph has at most L vertices. And the parameter will be K. Well, so here is example. For example, I have a graph and I have two vertices, and when I remove these two vertices, every connected component is of size at most 2. And when L is equal to 1, then this is again the vertex cover, right? Okay. I will give a kernel of L cube of size L cube k. And this is a not optimal kernel, so with slightly more advanced arguments, we can build L square times k, and with doing a little bit of more work, L times k. But I will give only L cube kernel. Yes. So how the kernel looks like? So I start from first from approximation algorithm. So what I mean by approximation algorithm here? So if I find some component of size more than L, what I'm doing, I just can pick up any vertex in this component, start building BFS tree, and as far as I have more than L vertices in this tree, I know that at least one. No, if I have a BFS tree of size L plus 1, I know that at least one vertex from this tree should go into the heating set. Right? So I just take all these L plus 1 vertices and put them in my solution. So this way I will have a L plus 1 approximate solution. Right? So I construct this L plus 1 approximate solution. If the size of this approximate solution is more than L plus 1 times k, I say no, I cannot have a solution at all here. And if it's or otherwise, I have this approximate solution here. Yes, and now I construct a bipartite graph. So now, so this one set here are the vertices of my approximate solution, and here. Every vertex corresponds to a connected component of the remaining part of the graph. Right? So this is every vertex here is a connected component, and every vertex here and the size of every connected component here is of at most L. And also I have a H from here to here if and only if the vertex from here has an H. From this vertex to some vertex in this connected component. Right. So this is the construction. Yes. So I am ready with to describe the kernelization algorithm. First of all, I do preprocessing rule. I delete all components in a graph G of size less than L. They never harm me, so this I'm done. So if I have, and now I construct this bipartite graph. So if the size of A times L is larger than B, we are done, right? Because look, every vertex in B corresponds to connected component of size, or corresponds to a graph with at most L vertices. So already here I have at most L squared times, so here I have L times K, L, and here I have L, so I have a L cube K vertices living here, so I'm happy, right? So otherwise, if the size of B is larger than L times A, I am using expansion lemma. I know that there should be some expansion living here. Okay. So there is expansion living here, but what does it mean, expansion here? So I have a L expansion. So I have this situation. Every guy here has L neighbors here, and no guy from here has a neighbor outside this set. So there's no neighbor of here coming to A. Okay, but so every guy from here is adjacent to L people here. So it means that I will have a star with L plus 1 vertices, that in the original graph, this will be a connected component of size more than L. Okay, so at least L, so exactly L pieces here connected by this vertex. So it means that I have to take at least one of these guys into the solution. And so I have all these pieces, and the only way I can do it, I have to take these people into the solution. So that's what I'm saying. So then I construct a new instance. So I remove, so if I found an expansion, then I remove these guys, and I remove all vertices living in the connected components, which are the neighbors of this of the set X into this graph. And then I reduce my instance correspondingly. Yes. So and just once again, what's happening? So either I already found that the size of my graph is at most L cubed times k, or if the size is larger, then I'm able to design a reduction rule, right? Which means that at the end, when my graph is irreducible, I have its size is bounded by L cubed times k. Okay, we're almost done here. So just a few more exercises. So if you want to play with crown decomposition, how it works, a good example to play to understand what's happening is to give a polynomial kernel for longest cycle parameterized by the vertex cover of a graph. What I mean by that, so I give you a graph, I give you a vertex cover of this graph of size k, and I ask if there exists a Hamiltonian cycle or if there exists a cycle in the graph of length at least L, but the size of the kernel, I want you to be polynomial on the size of the vertex cover. Right? And then the second also exercise for crown decomposition is called dual coloring, or it's n minus k coloring. So again, the input is graph G and the integer k, and I ask you if my graph contains a coloring with n minus k colors. And so if I ask if my graph has a k coloring, it doesn't make much sense because like 3 coloring is already NP complete. But n minus 3 coloring, it makes more sense from this perspective. Okay, and summing up. So we spoke about applications of classical matching theorems of Hall and Koenig's, how to apply them for constructing kernels. So one of the application was the crown decompositions, and the applications of crown decompositions were for vertex cover and for max SAT. Then we discussed a beta kernel for vertex cover based on Nemhauser-Trotter theorem. And then I went at very high speed through some extension of crown decomposition, its expansion lemma, and give an application for this for component order connectivity problem. And again, part of this is again in the parameterized algorithms books, and part of it is not. Yeah. Thank you.